Dr. Santosh,
Sir.
now you can preside the session.
Okay, thank you, sir. As my slide is visible,
It is visible.
change the slide.
Correct. Now it is changing.
Okay, thank you, sir. So, in our FDU today is the 7th lecture, and the coordinator Chitranjan Deo sir is my direct teacher. Since my BTech, he is guiding to me till now, each and every moment. Thank you very much, sir. Today we'll discuss about the recent advances and prospective insight into the powder mixed dielectric fluid of EDM. So here, when you think about our traditional EDM, then why non-traditional is there already? You have to know in between difference between the traditional machining and non-traditional machining. Then from that, the one of the widely used non-traditional machining is one is the EDM. Already you have to know all that things. So when you have to discuss in that things, then we have to think about choose about the materials. So here we have chosen the Inconel 718 is the material during the EDM. So here we have to see that what is the new technique we have to adapted here, and how we have add some powder materials in our genuine whatever the available the dielectric fluid in a normal EDM. Then what are the effect on the material? And the material is what means we have all the things on the material of Inconel 718. So first we have to think brief about the introduction of Inconel 8. Generally, the introduction of the Inconel the 718, it generally call it is the nickel chromium super based alloy. It having the high temperature resistance alloy and widely applicable in the aerospace, in the marine, the nuclear power generation, chemical, petrochemical process. So many where we have to use in our daily life also we have to use in the automobile sector like the silencer, flanges, then support grids, and also jet engine and suspension device, gas turbine blade, diffuser assembly, engine duct, all are the basically application of the Inconel 718. So here, so why we have to choose the Inconel 718 for the EDM process? Because already you have to know the Inconel 718 is the hard to cut material. So it is very difficult to machining about the traditional machining process. That's why you have to use the non-traditional machining process. Based on that, one is the our EDM process. So here again we have to show in the first line it is also the nickel chromium the Inconel 718 is also called the nickel chromium super based alloy. By viewing the table 1 we can see the chemical composition of Inconel 718. You have to see the Inconel the highest contribution is nickel, that having the percentage is 50 to 55%, and chromium is 70 to 21. That things the nickel and chromium that carries more than 70 to 75% of the rest of the uh, mixture. That's why it is called your nickel chromium superalloy. Then we have to see the microstructure of Inconel 718 in the figure. You can see very clearly. And again, it is very important why we have to go inside into the advance. Then what are the system we have to add some instrument for enhancing the traditional EDM, that things from the table 2. The table 2 you have to see the properties of Inconel 718. Either property you have to see density, specific gravity, everything is there. If you look into the thermal conductivity, then you have to see the thermal conductivity is only 11.4 watt per meter Kelvin. So here what, so 11.4 watt per meter Kelvin is very low thermal conductivity. So here the Inconel is very widely in everywhere in all the automobile section, then your marine, then aerospace everywhere, because it have the hard to cut material having also lightweight and non-magnetic and very low carbon, that is widely used. Again, we have to know, we have to use in the electro discharge machining. That means in EDM, whatever the material we can select, that should be electrically conductivity. Means if it is electrically conductivity, but our material thermal conductivity is very less here, 11.4. That's why we have think about some advanced technique, how we can machining the Inconel 718 or all the family of Inconel or titanium, then how we have to add some extra technique we will discuss here. So main focus here, whatever the material we have to take care here, that should be conductivity, but our conductivity is very low. Then for that, how to enhance, because in the EDM, here the material is removed due to the melting and evaporation. So melting and evaporation is depending on that spark, and the spark is again depending on that tool and workpiece. Again, here tool is generally you have to use the copper tool, but here workpiece having the less thermal conductivity, then how we have to increase the spark intensity towards the workpiece from the tool. We'll discuss here. In generally, you have to know the Inconel superalloy, that characteristics is very high strength, then good oxidation, then fatigue, keep resistance at high temperature. That's why we have used in every section here. But the work hardening tendency of Inconel, first thing. Then second is it's having the very poor thermal conductivity. Already I have discussed from the table number 2. And that result, due to that work hardening tendency, had poor thermal conductivity, so that resulted into enormous force while machining and producing high temperature field. And this material exhibit poor machinability, having in the term of excessive tool wear and interior surface finish. Therefore, Inconel is termed as difficult to cut. Another name of the Inconel is difficult to cut. But as compared to our conventional machining, the machinability of Inconel 718 is improved in some extent if the non-traditional machining route are adopted. That's why we have to use the EDM process. But, however, here low material removal efficiency and inferior surface finish, that is the very big disadvantage in any machining area, but especially in EDM. The main limitation is here low material removal and inferior surface finish, that restrict the wide application in the EDM for machining of Inconel 718 superalloy, so that we should eliminate the low material removal rate and inferior surface finish in our traditional EDM. That's why we have to adapt it. The EDM operation can further improve by adding some conductive powder or maybe semiconductive powder particles that into our dielectric fluid. Whatever the dielectric fluid is present in the normal EDM process, we have just add some powder particles, and the powder particles must have conductivity and semiconductivity that mix with the dielectric media. And this process that is for called powder mixed EDM. Then that powder particle, so in that principle of spark discharge in powder particle, we have to shown in this figure. So you have to see the tool, you have to provide the tool is the negative and workpiece is positive. Why you have to read the positive and negative, all of you know, because we have required the material removal from the workpiece. That's why workpiece has always the positive. But when you have to provide how you have to see the spark, because if you see the tool and workpiece initially, when the powder is, you have to think about the powder whisk medium. Initially, there is no powder, is the red line is the spark area, and the dot mark is there is the powder particle. Suppose you have to think that there is no powder particle is there. So how it will be performed and how it will be removed the material from the workpiece. So simply when you have to supply the electricity, your power, then the spark is generated in between the two electrode. It is one the tool and workpiece, and the spark is carried out from the tool towards your workpiece. Then the material will be able to remove. But here we have to know the spark is a discontinuous process. Getting then when we have to sparking and the spark is travel to from a tool to workpiece, and the spark is the discontinuous, and the intensity of spark is not uniform. That's why you have to get the result in the ununiform material removal from the workpiece, and the surface finish may be eroded. That is the limitation, and the material removal also very low due to our spark. The spark is a continuous and non-uniform applied onto your workpiece. For that limitation, we have to avoid it, so that we have to add some powder here, some metallic powder that should be mixed with our dielectric fluid. And when the powder particle are suspended in the between the tool and workpiece, here we have to see in the next figure very clearly. So here you have to show when you have to supply the power to the, then it is conducted by the tool. Then the spark is come, and the spark is come into the workpiece. Can you see? The red line of the all the arrow mark is the spark. So how the spark is spread throughout that area in between the tool and workpiece? Because when the spark is generated from the tool, so at that time the powder particle is presented in between the tool and workpiece, and the duty of the particle, that powder particle, they carried out the carriage, the charge from the tool to workpiece uniformly and bombardment on the workpiece. The charge is carried out uniformly throughout the all that powder particle is present in between the tool and workpiece. That's why a uniform spark, a uniform energy is bombardment onto the workpiece. If a uniform energy is bombardment on your workpiece, then whatever the material is removed from the workpiece, it should be uniform. And if the spark is uniform bombardment on the workpiece, it should be highly increased about the surface finish. That is the main limitation, was that low MRR and high RA value. So here RA value is slightly increases. So again you have to see the suspended powder particles. What are the suspended powder particles available in between the two electrodes? That helps the discharge to occur in a series of smaller distance, like zigzag fashion. Getting simply in before, when the powder particle is absent, the spark is directly bombardment onto your workpiece. The spark is not uniform. Based on that, the metal also remove. But here we can see a zigzag fashion, because all that spark is uniformly distributed by the help of that powder particle, and powder particle is act like a carrier of the spark from your tool to workpiece. So due to the breezing effect, a uniform distributed discharge takes place over a wide area of workpiece, and these facilitate it improve the machining rate, reduce tool wear, and appreciable surface finish. These what are the limitation is there in our traditional EDM, normal EDM. That's why we have to eliminate some extent by the help of adding some simply powder add into the dielectric. But when we have to add the dielectric fluid into the, when you have to add some material in dielectric fluid, we did not add it to whatever the tank is available in the DDM. That's why you have to especially set up a design. A box is we have to design. In that box we have to we have design a fixture, we have design a base, we have to also set a pump, then also you have to 30 years, circulating pump with nozzle, then one stirrer is required, then tag in your metallic tank, it may be glass, whatever maybe is there. So everything we have to make arrangement with a separate designed box. Then only we have make some work in the powder mist area, because you did not directly enter into your normal ATM process, because if you add some powder, they can be mixed into your reservoir tank of your EDM oil. Then you cannot change also, because when you have to add some powder, but he cannot change without the designer setup. That's why it should require some design setup for different changing. We can able to change the powder during the EDM process. We can see the effect. Also, we have to use here two powders. Then we will see what are the effect here. Here we can take a two part here, means part one and part two. In part one, we have to use, we have taken the workpiece as the Inconel 718 for the EDM, and using the graphite powder that should be mixed with our directory media. In part one, we have to use graphite powder. In part two, I will discuss. In that way, we have to use the silicon carbide. So in part one, here also we have to check the machinability. Then we can take care about the morphology and topology of the machine surface. How about your roughness, then crack density, then white layer thickness, residual stress, micro hardness, everything we can discuss. Then aspect all that material migration, formation of intermetallic compound, then grain refinement as affected by the EDM process. Also you have to take care. Then detailed analysis about the machining process. Then you have discussed all that thing. Then again, in the powder your experiment in part two, same thing. What are the discussed in part one? You have to add the graphite powder with EDM oil. So in next we have to use the silicon powder with kerosene. Here we have taken EDM oil. Here we have taken kerosene. So here powder is taken as here silicon carbide. In before we have taken graphite. Then also here we can take care some experiment like a line orthogonal array by the help of the utility theory. We will discuss all those things. So here it is the experimental set of the powder mist EDM. It should be required. Why it is required already I have discussed. So in that domain, you have to see the table 3 is clearly shown the domain of experiment that machining parameter is considered. Here only I varied the peak current. Only I have to vary because already you have to see, because all that in that experiment you can see so many process parameters that you can vary peak current, then pulse on time, pulse off time, the pulsing pressure, quality, all you can also vary here. But I cannot concentrate about the optimization here. I can concentrate here the effect of the material characterization, because optimization is different thing and material characterization is different thing. So I just focus on your characterization. That's why I have only vary the peak current, and rest all this parameter in table 4, all that parameter is there, all are kept constant, like gap voltage, pulse on time, pulse off time, flushing pressure, polarity, then spark gap, depth of cut, then powder concentration, everything polar concentration. I only vary the peak current. Again, why? Because whatever the process parameter is, they are available in the EDM area by the literature review or by the trial experiment. We have to conclude that the highest influence process parameter is peak current. Then only I have to vary what is the effect on the variation of peak current from 15, 20, 25, 30 ampere. Then we can see the effect. So here pulse on time, pulse off time. Then we have to see what is the pulse on time, what is pulse off time, what is flushing pressure. All you have to already have to know all that things. I just highlight about that things. You have to take the pulse on time. So during the pulse on time, so according to this name is pulse on time. On time means it is the on time of spark, because spark is a discontinuous process. When the spark is on, so during that spark on, it is how much time the spark is on, and in that time the material is able to remove by the help of the spark, and that time is called is pulse on time. Then pulse off time, So during the discontinuous process, when the spark is off, so why the off time is there about the 500 microsecond? Because why you have to put some off time? Because always if you increase the on time again high and decrease about the pulse off time, that's why the material will be removed more. But we cannot put large gap in between the pulse on time and pulse off time, because we have to know in our pulse off time is very useful by the help of the flushing pressure. So during the pulse off time, in off time, at that time the flushing will able to do their work. So whatever the machine, whatever the material is removed from during the pulse on time, whatever the your machine data, whatever the material is removed during the on time, that should be removed in the off time. Means before coming to on time, it should be clean out about the machine area by the help of your proper flushing. So if you did not provide some flushing here off time, or did not provide here proper flushing, then whatever the material is removed, that should not clean out from the machine area, and it is again there is chances from re-weld into the machine area. Then it will be again some effect is there. White layer thickness, it is called recast layer. We will discuss everything how it will be occur and how it should be minimized. Then flushing pressure, sorry, the duty of flushing pressure is just clean out the debris, whatever the material is removed from the one during the flushing area should be removed. Then about your polarity. Then polarity. So why it is polarity is there? Polarity you have to know the meaning of polarity. Then means why you have to put the positive and why you have to put the negative in the tool and workpiece. Already we have discussed. The spark, the depth of cut. Here you have to take depth of cut is as a constant, or you can take some time. So according to the machine, you can. I have taken the depth of constant here, and the powder concentration we have to add 6 gram per liters. And for the experimental detail, we have taken a plate that having the dimension is 50 into 50 into 5 mm about the length breadth. The square plate having the thickness is 5 mm. Die sinking EDM, that series is as shown in the slide. Then we have taken the EDM and the EDM oil and addition of graphite powder. And the graphite powder size is about 250 micron, or it may be called as mesh size, 60 mesh size, and the powder concentration is 6 gram per liter, taken the constant. So especially the design setup were arranged. So in that arrange we have setting of the submersible pump, steerer, pressure gauge, nozzle, all are used here, and this setup helps in improving the uniform distribution of the graphite powder within the dielectric cyclotronic system. Which again there is that maybe some limitation is there how the further research work, because if your dielectric within the dielectric fluid, if the powder is not properly mixed, because the property of that metal powder, it should be settled down in the bed, so that you have to use some styrer for circulating the powder during the machining. So after experimentation, we have you have to measure the MRR, then tool wear, then surface roughness, surface crack density, then white layer thickness. Then again, it is required some wing machine, then surface tester is required, then SCM is required, XRD machine is required, then finally we have tested some EDS. We discuss one by one. So by viewing the figure 4, you have to see the EDM wax surface of Inconel 718. That is the conventional EDM and graphite powder mist EDM. By viewing these two figures, we'll go in detail on that microscopical view. Only by viewing the two figures, that figure A and figure B, what are the view in the slide. So how you have to see the conventional EDM. So and another how after adding the graphite powder in the EDM oil, you have to see how the difference in the clarity and surface finish with respect to the normal EDM. Again, we have to see the surface crack density. It is a very important thing. The surface crack density, total crack length by the micro crack area. We have to from your SEM diagram. We have to one PDF exchanger we should raise that. From that we can measure all that crack density. So why you have to measure the crack? Because if you did not minimize the surface crack, it is the again one of the limitation of that machining area, because the crack is the initiation of the any failure of your metal. So it should be minimized. You have to take care about the surface crack density during the machining. Again, we will discuss about the white layer thickness. So how white layer thickness is there, the area of white layer that available, and what is the length of micrograph. We have to see in the figure. We will discuss one by one. Then we have to see about the experimental details in the SEM. Means why we have to use the micro hardness tester. Then again in part 2, I have discussed, I have taken the kerosene and powder silicon carbide. Everything is same. Just here we have to vary some powder concentration. Without power concentration, then 4 gram per liter, then 2 gram per liter. So here in part 2, we can see I can add up, instead of EDM oil, we can used here kerosene. So instead of graphite, we have used here silicon carbide powder. Then also you have to vary the concentration of the silicon carbide. And again, we have to see by the help of the L-line orthogonal array. Again, we have to compute that what is the MRR, array, surface crack density, all that things. So normally it is the in the second we have discussed in here we have taken the process parameter is there. IP we have discussed the IP is 25, 30, and 35. Then Paul salt time. Then we can vary the powder concentration. So here initially we have only vary the peak current, and here we have to vary peak current as well as Paulson time. Again we have to see that. So from that EDM process, the highest influence parameter is your peak current, and then Paulson times. So we can again we have to see what the concentration of the powder, and what of the rest is the remains constant. In that, see with the according to the DO, you have to see the MRR, RS, surface density, thickness. The value is there. Just we have to just concentrate about the. Now in the first result, I will discuss about the part 1. In the when you have to use the graphite powder means EDM, then you have to compare with your conventional EDM. So here we have to see first what are the powder we can take from your market. You have to just take test by your XRD, the graphite powder, but at the serine figure, and the average crystal size that should be calculated as the 28.92 nanometer by the help of that Scherer equation. And here that it must be noted that here also you have taken the so many different magnification here, the Scherer, and here the Scherer equation calculating the crystal size, and also the SEM micrographs. The different magnification are received the micro powder along in this figure. You can see by the figure. So here we can see the L equal to K lambda. So here L is the average length size we should calculate. Then here K is the safe factor. Then lambda is your wavelength, and beta is expressed as your broadening. That means your fluid maximum. It is called as FWHF. Then your theta is your Bragg's law. All of you know that equation from the physics to Bragg's law Scherer equation. From that it is also directly calculated by the equation we can got here. Then we can see the different magnification from the graphite powder. But you have to see the table number 6. So why you have to choose the graphite powder? Because here the thermal conductivity, just you have to see the thermal conductivity is 119 to 165 watt per Kelvin. Then its melting point is 3800 Kelvin. So whatever the workpiece we have taken, it is the Inconel 718, and the Inconel 718 thermal conductivity is 11 to 14 watt per meter Kelvin. Then due to that low thermal conductivity, that's why the intensity of spark from your tool to workpiece, it slightly less. That's why for energized and for utilize the total spark energy from tool towards the workpiece, it should be energized by the help of this graphite powder. That's why if the graphite powder is more thermal conductivity, then it should be easily carried from the tool to workpiece within some few times, and also reduce some times also. We have to reduce some machining time also by adding the thermal, by adding the powder like your graphite powder. Again, from the figure number 7, we can see the optimal image that exhibited the crater morphology of the EDM specimen at obtained. Then you can see very clearly what is the conventional EDM. Another figure is the graphical powder mist EDM, is figure A, and figure B. You can it is not very so clearly here, but some extent the surface morphology we can see here. In that surface in that surface integrity, like we can see it very clearly in the SEM figure. So in that SEM micrograph exhibit the irregularity, then we have to see what are the irregularity during the EDM work surface of our material with conventional EDM. So figure 1, what are the figure 1 is we have to show is the conventional EDM, and figure B is the graphical powder, is the graphite powder mist EDM when the current is 30, because we are 50, 20, 25, 30, so many current. I just have to pick the your SEM at the highest current, at the 30. So what is the effect? What is the SEM view of the when we have to, without adding the graphite powder, and after adding the graphite powder, how the visibility as shown in the figure we can see very clearly also here. But you see in figure A, the surface irregularity like crater, globules, the crater morphology, then globules of debris, then melted material deposition, then some spherical deposition, spoke mark, is also called chimney, cracks, white layer thickness, and etc. That also describe in the EDM surfaces. And in other hand, also in the topographical, that means that should be measurable and quantified. It should be measurable and quantifiable. That things is your surface layer density, then white layer thickness, residual stress, then micro indentance, hardness, along with the metallurgical influence, all that phenomena, and that the grain repairment, then strain effect, and all that things we can carry it out. You can see how by small amount of powder, when you have to add it into the dielectric, then how we have to significance minimize the debris, the cracks. Yes, crack is there, but severity of crack is clearly visible deterioration when you have to add graphite fluid, and some extent the metal deposition is there. It should be eliminated everything by adding of the by use of your graphite powders. So here also we have some comparison in between the conventional EDM. So here have to see some slab of crater is there, large diameter of globule is there, everything in so in that figure, and also some wide and shallow crater that enhance the surface finish specimen by the adding of the powder mix EDM. All that things, it should be eliminated by the help of the graphite powders. Again, also you have to see the focus on the severity of crackness. Which again we have to see, if you again enclose in the SEM, in that figure you have to see the SEM micrograph that exhibit severity of crackness, because so many limitation is there. Just we have to think the crack, because the crack is the highest influence on the defect of the EDM is there. That should be minimized, because crack is the initiation of your any failure. It should be minimized. That's why you have to see in conventional EDM, so what is the intensity of crack and what is the intensity of crack by after adding the graphite powder at the current of 30 amperes. See again, so here that analysis is revealed that the machining surface produced by your conventional EDM was consisted of the globule, debris, surface crack, and in the all that abundant and while compound in these things that should be removed in that powder mix EDM. And the severity of surface cracking is very important. The severity of surface cracking, that means the crack opening width was also found relatively high for in case of conventional EDM, but shown in the figure A. Since when we have to add the graphite powder, again we have to know due to their conductivity, because our material conductivity is almost very less, 11 to only 14, but here our thermal conductivity is marginally 100 times increase of your thermal conductivity, like your powder, your graphite powder, that carries also some amount of heat, that should with some amount of heat away from the machined area during the machine. Also you have to know in that traditional machining and unconventional machining, so during the machining some temperature also develop, or due to the temperature difference, because dielectric because your workpiece is present in between the directly, but due to the difference between the temperature, the crack will be initiated. So for avoiding the localized increased temperature, the powder particle not only act like the carrier of the spark, also it act, they have some soak, and they can some amount of heat energy, they soak some heat energy from the machined area, and this extent of thermal stresses developed at the machining surface was relatively less magnitude. Due to that, they may be there, but the magnitude will be less, and this reduces the degree of severity of surface cracking. So again, that is another duty of the ear powder, that only not only the duty of ear carrier the spark, that also duty they have to soak some localized temperature during the machining. For that, we can minimize that magnitude of the developed stress, also that minimize the severity of the crack. Again, in this figure, we have to discuss about that SEM micrograph, that exhibit the existence of the white layer thickness onto on the top surface of the machine surface. In that figure A, in left side is the conventional ADM. You have to measure the white layer thickness is some about the 31, and in after graphite we have to by adding the graphite powder, we have to see the white layer thickness is increases. But again, we have to think know that the white layer thickness is increases. It is the one type of limitation. But due to the addition of the graphite, it should be here increase. Because why? Because what are the generated of debris within the work? Moreover, the debris might somewhat be restricted, because here we have to add some powder particle in between the tool and workpiece. So why I just focus onto the why the white layer thickness will be increased, because after adding the powder particles we have get so many advantages. But here we have to see what is the limitation is, that they can increase the white layer thickness. So white layer thickness or the recast layer is nothing but whatever we have discussed in our BTech level or MTech level in traditionally in our single point cutting tool. What you have to hard that the built-up edge. So what is built-up edge? Just you have to so back into your manufacturing science too, into the BTech level or MTech level. So the built-up edge is formation during a single point cutting tool in the rack face. When the chip is flowing onto your rack face, then some powder particle stick onto the rack face, and due to the local temperature and due to the friction in between the chip and to the rack face, then some amount of powder particle stick onto the rack face. Then by adding, then it is called is your built-up edge. Same case, is here in the EDM. So due to the improper flossing, and due to some insufficient T of time, so that T of time is not sufficient for floss away, or the flossing pressure, but the flossing pressure is available. If it is not sufficient, properly clean away or floss away what are the debris formation during the machining process. So again that debris and again that removed material is stick into your machining area, and during the T on, again it is re-welded onto your machine surface, and again it is increased by layer by layer, layer by layer. It is called as white layer thickness, and it is also called recast layer. So again it is limitation, and when the recast layer is formation, then again it is required more time for melting out the recast layer thickness. Also you have to know, so what is your hardness of your welding. So that is the welded means after welding it is more harder than your parent material. Here is same thing. So here the hardness of your white layer thickness is again it is more hard regarding to your parent materials. So during the machining, you just remove the material of your white layer, then only they can remove your parent material. It requires more power. It also requires more time for removing the material. So here, due to that white layer thickness, we have consuming more energy. We have consuming more machining here, more machining time also. So how? So why it is possible? Because it is very advantage by adding of your powder. Because in this case we have make some disadvantage here. So why it may possible? So the movement of debris. Another is movement of debris. Another and somewhat it may be restricted due to the presence of your local agglomeration powder within the dielectric medium. And due to the insufficient flossing and the debris got stuck onto your machine surface, that formation deeper to deeper white layer. So it should be only minimized by using of proper T of time and proper flossing. Then we have to see the figure shows that the XRD analysis. So in that XRD spectra from the EDM work surface of Inconel 718 that produced at the current at the time of the current is about the 30 ampere obtained through the conventional EDM. Just you have to take the XRD analysis, the metallurgical characteristics. This XRD analysis that carried out, so identification of various phases. So we have to do that things. So various phases present within the machine surface along with the precipitants. The extent of grain refinement taking place during the EDM operation was also understood by comparing our peak current, here peak pattern, what are the peak pattern as shown in the figure, peak pattern of the machine surface, while compared to that received parent material. So here we can see about the peak of your parent material, and here we have to see the XRD spectra of the EDM work surface. One is your received work surface, another is your EDM work surface by adding the graphite powder. So while we have to comparing the XRD spectra the received in Inconel 718 to that the EDS specimen, you have to see the figure, and also you have to see when you have to add in the graphite powder machine EDM that increase the thermal conductivity of the working medium. That's why you have to use this graphite powder. And also it is possible due to its enlarged spark gap, and that causes and that results that heat to be distributed uniformly into your working zone. And moreover, the multiple discharge take place for a longer period of time. And this is done promotes the grain refinement of the large extent. and the refined gain structure also take place, relieving the thermal residual stresses. Already we have discussed this part. So again, and in powder mist EDM, some extent of amount that residual stresses is also released due to the mechanical abrasion effect on the powder particle on the surface, and therefore the property of here that crack formation is remarkably reduced in the powder mist EDM, and you have to got here refined specimen also. We can calculate about the crystallite size, the microstrand dislocation theory, and here you have to see the EDS analysis. So here figure see the EDS result from the EDM'd wire surface. What are the material by our conventional EDM and the current of here 20 ampere. Then again you have to see in that figure the EDS that result, the EDM of the wire surface of the in 7 watt that produce at IT that IP equal to 25 ampere. Well, you have to add the graphite powder mist EDM. By viewing the two graph in EDS analysis, we can conclude that the mainly in the right side you have to see so many composition you can available is there, carbon, aluminum, something is there, and here is there, and we can see the significance. One is carbon is significantly very high during the powder mist EDM. So from that EDS analysis, it was observed that while compared to our received Inconel 718, the EDM wire surface obtained through the conventional EDM as well as the powder mist both exhibit relatively high carbon content. This basically consequence of the dielectric cracking. It is also known as paralysis of the dielectric fluid, which promotes the carbon migrants at the machine surface. Already during the machine, we have to increase the carbon content, and during again the paralysis or due to the dielectric cracking, because in again we have to create some here carbon content. That's why the EDM analysis revealed that the amount of carbon enriched was not uniform throughout the area. That's why here carbon content is slightly increases, and apart from this, that localized phenomena, it could be also conclude that the graphite powder mist EDM that result the less carbon migration onto your machine surface. Well, you have to compare the conventional EDM. So this turned to reduce the probability of formation of hard carbide particles at the machine surface, and thus that reduce the percent that severity of your cracking also. And this might be due to the lesser extent of the dielectric cracking during the spark discharge, as addition of the conductive powders that reduce the dielectric strength of the working medium, and thus it is stimulated the early discharge to take place. And moreover, the discharge, the energy, whatever the discharge energy was uniformly distributed at the energy zone, which resulted into the heat dissipation in the more favorable manner from the discharge zone during our pulse of times. Then again, we have to see what is the effect of peak discharge current on MRR. So in that figure, we can clearly see that in the figure, the black in that figure, that is the relation in between the material renewable rate with respect to peak current, because in the part one already only we have to take the one variable as the peak current is the 15, 20, 25 and 30. For the four position we have to see the MRR. We can see the energy intensity is directly proportional to your rate of material renewable. Always you have to know the intensity of energy is directly proportional to the MRR. So here MRR is increases by default if the peak current is increases, means energy, the intensity of energy is increases by default. Energy here MRR also increases in the both figure. MRR increases, but you have to see the black line is the conventional EDM, and the graphite powder mist EDM is the particular graphite powder here EDM. So here MRR is little bit high in comparison to this thing, and it should be smooth in comparison to the conventional EDM. So that effect of that peak discharge current resultant into the increase the material due bar lead, because the peak current is the directly proportional to the energy input. So we have energy input that is the 15, 20, 25, 30. So more material was eroded from the workpiece, leading to improve this MRR. So increase the MRR with respect to increase the peak current was found more in case of graphite powder. That's what we are shown in figure clearly. So again, when by adding the graphite powder, by helping some here bridging effect that carried the some interlocking among these powder particles, and thus they behave like a chain under the sparking area. So the sparking intensity is remarkably increased within a discharge, leading to a faster erosion from the work surface and consequently improve the also MRR. That's why this MRR is little bit increased by the help of the graphite powders. Again, in figure number 14, again we have to see the pink line is the graphite powder mix EDM, and the black line we have to see that with our conventional EDM. So here also you have to see that how we have to our roughness value here RA will be relation in between with respect to the current. Again, by intensity of the spark, the intensity of energy, it will increases with the metal here. MRI also increases, and here RA value is also depending on your intensity of spark. If intensity is more, also RA value will be increases. So again, you have to see the smoothness line of your RA, because in RA is your surface finish. Your surface finish would be means whatever the metal will be eroded, that should be here also RA is increases. In your graphite powder in the peak line is increases from your 15 to 30, and by your conventional EDM, the black line also increases from 15 to 30. But these two lines you have to see how they can smoothly, the pink line how smoothly increases from 15 to 20, the 25 to 30. Then how then whatever the smoothness line of the black line, that is the conventional EDM, that should be increases of your array. But how the smoothness, because the intensity of spark is not uniform, that shows in the RA value, and it shows in the smoothness in this figure also. So these are, so here in this figure 14 shows that the abrasive powder present in the dielectric media also enhance the material removal rate, which is simultaneously influenced by the mechanical thrust study you have to see in the last figure. But here this also facilitate the dislodging of the work material from the work surface, the speeding of your material removal rate due to increase the your current, that should be speeding of the MRR as compared to the our conventional EDM. So during the powder mist EDM, increase the peak current. That means which is the function of your energy input, means increase the energy input, produced higher degree of explosive effect imposed by the abrasive powder particles, and this result into increases the rate of material removal rate, also that impact into your RA value. So again here you have to see in the improvement of your MRR in powder mist EDM was appeared insufficient as compared to our conventional EDM, and this might be due to why we have to see this lagging. So this might be due to the fact of local agglomeration of the powder particle, which restrict the removal of your eroded material from the machined zone, and this eroded material thus again accumulated and got engaged in the rubbing action with the machining surface. And that was the reason why the surface finish of the powder mist EDM was appreciably remarkable, more apparently as compared to our conventional EDM. And again, you have to see in the figure number 15 the effect of peak discharge current. Also, you have to, done that event of peak discharge current on our TWR, then your MRR, then your surface finish. Then you have to know about your crack. Then again, we have to know that it should be minimum to minimum. That is the your surface crack density is about some value is there 0.0113, and after adding some your graphite powder, you have to see the surface crack density is almost about 0.0106. That should be minimized by viewing this figure. By viewing the figure A, B, and C, D. By viewing this figure A, B. So A is the surface cracking by the when the measure the surface crack density, we can when the 15 ampere is there, and figure B at the 25. So again in the figure CD, it is again the 15 ampere and 25 ampere by adding the graphite powder. A, B is without adding the graphite powder. We have to check the severity of cracking. And again in the C and D, it is the 15 and 20. Again we have to see what is the means how the surface crack is depending on your intensity of your power. So due to additional powder particles, the discharge gap is enlarged, and which reduces the gap voltage as well as insulating the strength of the dielectric medium. This discharge, what are the discharge energy is evenly facilitate formation of uniform, distributed, and wide and shallow crater. So the crater gap. Thus, the excellent surface finish we have to obtain in the figure C and D. Often, this abrasion effect of the powder particle at the work surface may also contribute toward the enhanced surface finish, such as the abrasive action help to reducing the deposition of debris and also that all dilution of your cracker boundary. So again, our powder is also helpful. That should be again one type of carrier that should be strike onto your debris, and so due to the strike by the help of the powder, the debris should be cleaned out. Again, the another duty of that powders. And in that graphite powder mix EDM, the low density of graphite powder could be mixed uniformly with the dielectric media and that flowed very easily. Why you have to use the graphite powder? Graphite powder is very light, that should be flow very easily, and result into that outstanding lubrication property of the graphite powder mix, and that might be favorable influence the surface finish to be appreciable. So, due to the effect of that current on the surface crack density, you have to see, and in the figure AB is comparison to CD, increment of the peak current consequently increase the energy input to the workpiece. That resulted into evaluation of the huge thermal stress, and when induced thermal stress is exceed that ultimate tensile strength of the EDM surface, then crack do initiation. Already you have to know the definition of your crack, how the crack is initiated. And the crack is initiated and propagate over the surface. Once the crack is initiated, then they propagate towards this end. And often they penetrate throughout the depth of white layer and continue towards the block of parent material. So here the crack density was found relatively less in the figure of C and D. So again we have to see in our powder mix EDM. So when the abrasive powder particle is carried sufficient amounts of another duty, when the powder particle again they have to soak and carried out some sufficient energy that should be generated during the machining process. So that wider spark gap facilitate the easy removal of the eroded material that debris which are already carried out some amount of heat also. So they also use for your clean out the debris. They also use some carry out the heat from your machine zone. Therefore, the transfer of the heat by the conductive abrasive particle is balanced by the rapid cooling of your workpiece. Thus, the machining surface produces by your powder mix experience relatively less thermal stresses in a comparison to our conventional EDM. So due to that reduced residual stresses, that might be the largest extent of your grain refinement, and thereby relieving the residual stresses to some extent. And finally, you have to see the surface scraping of your lesser extent has contributed to your superior surface finish. Again, we have to see in the figure what is the effect of the peak discharge current on the white layer. In the white layer, the conventional EDM, you have to see you have to measure the white layer thickness. Also, if you again increase the white layer thickness, it should be on the limitation of our machining process. It should be minimized. But you have to see here they have taken your 3-year conventional 3-year without powder mix. Current is vary from 15, second is 20, then 30. Then again by the adding of your powder mix EDM, then we have to then same variation of your current 15, 20, and 30. Then you can simply increase the white layer thickness after adding the graphite powder. So here we can see the thickness here. So here the increased the energy input that causes more material removed from your workpiece, but dielectric fluid appear increasingly inefficient to sweep away the debris from the machine zone. Again, due to that white layer thickness, again it is the obstruction because when the formation of white layer thickness is there, the layer is uneven. The layer is not uniform because we have to know about your comparative your built up edge because white layer is built unevenly, so RA value will be increases if your roughness peak to valley is there. So within the gap between peak to valley, some your debris is present in their block area. That should not possible to remove by our flossing pressure. It should be removed, but we have to minimize some extent that removing that flossing area. So due to that, due to the dielectric fluid appearing the increasingly inefficient sweep out the debris from the machine zone. Hence, the molten metal get re-solidified, forming the white layer that adhere onto the machining surface. Thus, white layer appear increases thicker to thicker as discharge current is increased gradually. So since during the execution of the powder mix EDM, the graphite powder owing their thermal conductivity, then carry percentage of discharge of heat energy, it was expected that surface finish will be appreciably slightly high. And again, so how again we have to compare to our conventional EDM, how we have to minimize the built-up edge. Again, we have to see the how we have to minimize the recast layer and how we have to minimize the white layer thickness. And so again, the causes of your white layer is, if you know these causes, then only you have to conclude that how we have to eliminate that causes, how you have to eliminate that things. So this might be due to the localized effect of the agglomeration of the excess powder near the gap in between the electrode. And again, if the powder will be excess, because in that experiment in your part 2 we have discussed the concentration of different powder. If you think if you add some powder, then it will be remove the more material, the intensity spark will be more uniform, but it have some limit. That's why in part 2 we have discussed we have to optimize how much concentration will you have to provide it during the machining process, how much powder you have to add it. So concentration, so one experiment also you have to float if time be available. I will discuss it in detail in part 2. So here, if you increase the concentration more than optimum value, you have to know what the meaning of your optimization, what the meaning of your optimum value. So if you increase the more than the optimum value and that excessive amount of powder particle when exceed that optimum value and that powder particle is suspended onto the in between the electrode, in between the tool and workpiece, and it also restricted the debris from flushing out properly when it is a barrier. In year before you're optimizing adding of your concentration of your powder, it should be useful one. If the concentration will be increases, again it will be reverse. It also restricted the flushing from the properly due to the presence of that excessive powder in between the tool and workpiece. Again, that flushing duty, what are the flushing pressure is applied onto that machined area. That duty they have to flush out the debris as well as that pressure is also restricted by the more concentration of the powder also. Therefore, the debris has remained in that same state for a longer period of time. Again, it is solidified after some time during the machining. However, after some time, they can deposit uniformly deposited onto our machine surface, and it should be thinner to than the thinner water thickness when compared to the EDM. So that's why in our conventional EDM, in your powder mesh EDM, the thickness, your thickness is increases in the powder mesh EDM as compared to our conventional EDM. So during our EDM, the intense heat generation due to the spark discharge, already you have to know. So material removal is caused due to the melting and evaporation of the workpiece. However, the spark is not only melt the workpiece but also melt the tool. When the intensity is increases, again they affect our tool also. We have discussed about the tool wear rate. Then again, the melting tool is called as your electrode wear. Then we have to see the effect of the TWR with respect to our current. So again, we have to see if the current, if your intensity of current is increases, intensity of power is increases, then not only that MRR is increases from the workpiece, but also we have lose the life of our tool also. Then again, you have to see in the green mark, either graphite powder mesh EDM, then is black line is your conventional EDM. Then again, we have to see our tool wear is less, while you have to adding about the graphite powder mesh EDM as compared to our conventional EDM. Again, you have to see in the black line how the TWR, how the wear rate of the tool of the EDM is deteriorate. It is not smoothly. You have to see from 15 to 20, then 25. Again, unevenly you did in your 25, in your 30. So it is unevenly. So here the line is also is not as smooth. So for that we can conclude that we can increase the roughness and lose the material also from your tool. So again, we can save our tool also by adding the graphite powder in our EDM, and whatever the tool wear rate is there in the tool, it should be smooth. That should be wear must be occur. It should be minimum, but you have to get the smooth wear. That's also you have to get the surface finish will not deteriorate of your TWR, because we have to know that in the EDM process, what is the surface of the face of the tool that should be reflect onto our workpiece, and that should be very clean and more array value on your tool also. Then again, you have to see it as notice. You have to see the notice that here tool also wear sufficiently where compared to our conventional EDM. The tool wear rate is also enhanced. The tool wear rate is lesser extent in enhance of your tool life. So during this operation, heat is mainly transferred to both workpiece as well as tool. Always we have to know in our conventional machining process also, so heat generation is there, how much amount of heat is carried by chip, how much heat is carried by your tool workpiece. Already have discussed in your conventional EDM. In your conventional machining, in your EDM also, heat generation is occur. There should be some amount of heat is carried out by your chip, means your the debris then some amount of heat is carried out by tool, and some is carried out by your workpiece. So always we have to know from our traditional machining also, less amount of heat is carried out by your towards your tool, because tool is your precision things. So here during this operation, heat is mainly transferred from both the workpiece and your tool. So pyrolysis of your your dielectric medium generate the pyrolytic carbon, which is adhere onto the workpiece, as well as whatever the carbon will be generation during the pyrolysis effect that adhere onto the workpiece, also it is adhered into your bottom edge of your electrode, bottom edge of your tool. That's why in every machining, while you have to measure the TWR, at that time it should be clean the face of your tool before second machining. Before second machining, it should be properly clean, because so many carbon particle is also present stick onto your tool face. And that deposition of your hard and low carbide layer in turn that reduces our thermal conductivity of our tool. So this consequence of your rapid tool, if that restrict the energy of your tool, if they restrict the spark, then the heat generation will be more, within the tool, due to not properly transmitting the spark from your tool to workpiece. Then the tool must be heated off. It will be cleaned properly, then the heat must be transferred from your tool face towards your dielectric or into your powders. So it will be restricted by the some local carbon divided onto your tool face. It should be minimized. So again, it should be minimized by the help of our. So therefore, the heat transfer take place through your bulk of yielded material, not only overcoming this. So that's why by help of your powder particle, it should be less as compared to our conventional EDM. Again, we have to see some crystal size. So here we have to conclude that only have to conclude the part one. Only have discussed the your graphite powder, the intensity of the graphite powder. So use of your graphite powder at average size, what are the your 60 mesh size or 250 microns added to the dielectric media with the powder concentration. The constant is 6 gram per liter is found beneficially than conventional EDM due to the improve our MRR, reduce the tool wear rate and superior surface finish, and reduce degree of surface cracking. Again, we can conclude that some maximum improvement in the MRR was observed at 30 ampere. Then more satisfactory surface finish we can get at the current while the is 20 ampere, and the minimum tool wear we can get at the ampere of your when the current is 30. As compared to the conventional EDM, the thickness of white layer is found relatively more in case of powder mesh EDM, because due to that insufficient flossing due to the agglomeration of the of your localized agglomeration of the graphite powder, that might restrict the eroded material or debris to be carried out efficiently, and this leads to enormous of your white layer thickness. And the lesser extent, again we have to see in your exactly the lesser extent of your carbon migration that can be carried out during the powder mesh EDM, that should reduces the hard carbide powder like shown in here and form in the machine surface, and that consequently suspend the potential on the formation of your severe crack. And also this can be minimized, this hardness can be minimized by adding of your powder mesh EDM, because this thing cause of your crack. Also you have to know how the crack is a highly limitation of your of the any manufacturing area, and the specimen produces by the powder mix EDM exhibits relatively less micro hardness as compared to the residual stress as well as compared to our conventional EDM. So finally, for the case of graphite powder mix EDM of Inconel 718, the grain refinement of your greater extent was observed at the machine surface while compared in the case of conventional EDM. So it is all that I have to concluded about my the first part. Then next year, second part is there. That is area is there. Is how the silicon carbide is there, and in that silicon carbide, I have to taken the kerosene, and again in that case, the silicon carbide I have taken the different concentrations at that time. So time is not permit to me because only 8 minutes is left. That's why I have not discussed about your part two. So part two is not able to. At that time, we may be able to see in next time how the effect of the concentration of the powder medium. So for that, I conclude here and thank you. If any doubt, you ask me.
Participant, do you have any doubt? Then you can ask Dr. Santosh Sahu.
Okay, thank you.
Okay, I like to extend my thanks to my colleague and co-coordinator of this program, Dr. Sahu, for delivering a wonderful session on powder mix EDM. He has explained different aspects of EDM process and also deeply insight and spotlight the different areas in powder mix EDM, how it is different from the non-conventional or general EDM process. So again, I thanks to Dr. Sahu for delivering this lecture, and I request all the participants to join in the last session of today's by 2:45 p.m. Professor Dikshit will deliver the lecture. Thank you.
Okay, thank you, sir.